So in this video, we're now going to consider what happens if we have that capacitor in our input network instead of in our feedback network. So let's start by looking at it mathematically, and then at the end of the video, we'll come back and we'll talk about it qualitatively in terms of our capacitor behavior, as we did with the capacitor in the feedback network. So in this case, we see that our input impedance, Zi, is equal to the series combination of our Ri and the impedance of our capacitor, which is 1 over J omega Ci. Our feedback impedance, Zf, is just going to be that resistor, R sub f. And again, because this form matches the general form that we had a couple videos back, we can say that our transfer function, J omega, in general is still equal to negative Zf divided by Zi, because we have an inverting amplifier configuration. So plugging in our values for Zf and Zi, what we have is just a negative Rf in the numerator, and in the denominator we have Ri plus the quantity of 1 over J omega Ci. So let's clean this up a little bit so it's easier to see, and we can do that by multiplying the numerator and denominator by J omega Ci. And so what that's going to do is that's going to get the J omega Ci out of the denominator down in the bottom there. So if we do that, we see that this is equal to negative J omega Ci times Rf divided by 1 plus J omega Ci times Ri. And so again, we can make a few observations here. We can either go back and we can compare to some of the general forms we saw for our first order filters with our passive filters and compare to that, or we could go through doing our extreme cases again. So let's just sort of verbally, without writing down, look at this briefly. We can say, of course, if our omega is 0, we're going to have 0 divided by 1 plus 0, so that's going to be a 0. If our omega is going towards infinity, we're going to have a negative infinity over infinity. It's the same form. We could do L'Hopital's rule to be sort of mathematically correct, but that's going to give us a 1. And so the reason we can ignore this negative sign is, remember, we would be interested in the magnitude of our h of j omega. We could also go back and we could compare to what we had previously seen. So if you look on page 5-3 in the notes, we had previously seen an equation like that. And so what that tells us is that this has the same form, which means it is a high-pass filter. So looking at that then, we can figure out what our high frequency gain is. So we want to know now what our high frequency gain is. So our low frequency gain, of course, is going to be 0 because it's blocking it. But our high frequency gain is going to be when we have our really large omegas. And so what we can see is the omegas are going to cancel out, our C's are going to cancel out, and we're just going to be left with negative Rf over Ri. So we have negative Rf over Ri. So it's a high pass filter, and here is our high frequency gain. One other thing that we can sort of determine of interest is our corner frequency. And so it's easiest to do this by inspection. So comparing that to our previous equation on page 5-3, we can say our corner frequency for this equation is going to be 1 divided by Ri times Ci. And so again, we could go through that whole argument where we say we know at this corner frequency the magnitude of h of j omega is equal to 1 over root 2, and then solve for omega c. But oftentimes we can just compare to a previous result. So that's sort of our in detail mathematical description, but let's take a qualitative look at our circuit here. And again, keeping in mind that the impedance of our capacitor is equal to 1 over J omega C. And we can say, as we said in the previous video, for omega equals 0, our capacitor is acting like an open circuit. And as our omega is getting really large, so omega equals infinity, our capacitor is acting like a short circuit. And so we can we can sort of verify those two relations by considering our capacitor impedance equation here. So if we have and so one other thing, let me write down up here as well. So remember, our overall transfer function is given by this negative ZF over ZI. So let's consider our case of zero frequency. So zero frequency, this capacitor behaves like an open circuit. So our RI and our V input are not even connected then to our circuit. And if we look over here, basically our RI is going to be infinity because we have this open circuit, there's no path. So that's going to mean our transfer function is of course 0. Now if we have our high frequency case, our capacitor is acting like a short circuit. So now we have something that looks like this, in which case this is just our inverting amplifier configuration from our op-amps unit. So of course our high frequency gain is just going to be the RF over RI as we had determined in the previous unit. So again, it's always important to keep in mind there's not necessarily one correct approach. Depending on the situation, you might need to do this more detailed mathematics, but it also might be sufficient in some cases to do sort of a qualitative look at the circuit to determine what's going on.